Hello students, welcome to Pecho Virtual School PVS. My name is Ronald and welcome you to this lesson of physics. Our topic today is a current, electricity, or simply electricity. Here I'm showing you pictures of an electrician has climbed the pole trying to fix a wire there. Also about electric current, these are just simple electric sparks, and a very simple circuit here. These are some of the things that we shall meet in our topic of current, electricity, and you know how important electricity is to our homes and to our lives. What is current, electricity? Or what is current? Current is just simply the study of electric charges in motion. Electric charges in motion. You should have looked at electrostatics or static electricity, which is the study of charges at rest. Now we move from that topic to study of charges in motion, which is current, electricity. But what is an electric charge? An electric charge is a physical property of matter that causes it to experience a force when placed in an electromagnetic field. Electromagnetic field is the combination of the electric field and the magnetic field. Now, when this particle is placed in that field, it will experience a force. That particle that experiences a force is called electric charge. Electric current. Before we go further, let us know what electric current is. Electric current is the amount of charge flowing through a conductor per second, or the quantity of charge flowing through a conductor per second. That is our definition of electric current. Or we can simply define it as the rate of flow of charge through a conductor. The rate of flow of charge through a conductor. The term or the word rate here simply means that the quantity of charge is divided by time. And like we said, per second, that means this charge will be divided by the time, and we shall get per second. And here also we can say the rate of flow of charge through the conductor. And from here you can now get the formula that I, which is the current, is equal to the quantity of charge Q over the time T. And if we make Q the subject of this formula, then we cross multiply I with T, and we get Q equal to I times T. So what's the unit of current? Alright. The unit of current. Current is measured in ampere. You need to practice that. Ampere. An ampere. Ampere, the symbol is capital A. And what is an ampere? An ampere is the current in the conductor when 1 coulomb of charge flows through it in 1 second. That current which will pass through a point when 1 coulomb of charge passes there in 1 second is an ampere. Current an ampere is the current in a conductor when 1 coulomb of charge flows through it in 1 second. So when 1 coulomb of this charge is passed through in a conductor in just 1 second, the current that will have passed through that conductor will be 1 ampere, and that is an ampere. Using that formula, we can have examples. Let's start with example 1. A charge of 2550 coulombs flows past a point in a circuit in 25 minutes. Find the current flowing. So we are given the charge and we are given the time. Now charge is this and the time is 25 minutes. Now you realize that from our definition we said per second, but here it is minutes. So we have to convert the time, convert this time to second. Now the time must be in seconds, and the SI unit of time. So we know time will now be 25 times 60. Why 60? Because in 1 minute there are 60 seconds. So if I have 25 minutes, then I will have 25 times 60 seconds to get 1500 seconds. So having converted, now we can quote our formula of I is equal to Q over T, and we substitute, and we get the value of I as we get 2550 divided by 1500, and the current is 1.7 amperes. A, capital A, 1.7 amperes. That is our first example, where the time was in minutes has to be converted to seconds. Example 2. A current of 2.0 amperes flows through a conductor in 40 seconds. Find the quantity of charge flowing through a conductor. So the current is given as 2 amperes and the time as 40. Here there is no need to convert, as everything is given in its unit. Remember the formula, I is equal to Q over T. If we make Q the subject, we get I times T. So substituting our values, I will be 2 times 40, and we get charge Q equal to 80 coulombs. This capital C stands for the unit of charge, which is a coulomb. 80 coulombs. Now from that, number 3, a charge of 1200 microcoulomb, again the symbol here stands for micro, is obtained when a current of 40 milliamperes is passed through a wire. Find the time taken for current to flow through the wire. So again from here we are given the charge in microcoulomb, 1200 micro. The micro symbol here simply means that these are small quantities, these are smaller quantities, whereby it is times 10 power negative 6 times 10 power negative 6. That is what micro stands for. So we shall say Q is equal to 1200 times 10 power negative 6 coulombs, and I is in milliamperes. So milliamperes, milli means times 10 to the power negative 3. So we have 40 milliamperes will be the same as 40 times 10 to the power negative 3. So these have to be converted to the standard unit, which is ampere, or the standard unit, which is a coulomb. So when we now quote our formula, Q is equal to I times T, and then we substitute. This is the value of the charge, and this is the value of the time. So if make T the subject of the formula, T will be, or the expression, we shall have 1200 times 10 power negative 6 over 40 times 10 power negative 3, and then the final answer will be 0.03 seconds. So I brought this example here to try to make you also get used to smaller units of current, micro and milli. You have to know that they have to be changed to amperes and multiplied by those factors, change to amperes and to coulombs. Okay, having understood the definition of current and its formula, we are now subjected to this simple exercise of 3 numbers to work out. So please, you work out these numbers. A charge of 420 coulombs flows past a point in a circuit in 20 seconds. Find the current flowing. So you can work out number 1, number 2 and number 3. Okay, now let us look at resistance and potential difference, PD. Resistance and potential difference, PD. What is resistance? From the word to resist. Resist means to oppose, to object. Even the conductors offer some resistance to the flow of current. So resistance, we shall simply define it as the opposition to the flow of electric current in a conductor. The opposition to the flow of electric current in a conductor. And it is measured in ohms. Practice that unit, ohms. Ohms. The symbol of ohm is this. Okay, this is the symbol of ohm, or omega. This is the symbol for ohm. So that's the unit. What is an ohm? An ohm is the resistance of a conductor to current of 1 ampere when the PD across the ends of the conductor is 1 volt. Now when the PD is 1 volt and supplies current of 1 ampere through that conductor will experience a resistance of 1 ohm, or that current will experience a resistance of 1 ohm. So therefore we simply define an ohm as the resistance of a conductor to current of 1 ampere when a potential difference across the ends of the conductor is 1 volt. Good. As you're aware, with units, you start the unit by measuring the physical quantity measures. Like here we said an ohm is the resistance. For example, Pascal, if we say Pascal is the pressure, since it is a unit of pressure, a joule is the work done. So even here an ohm is the resistance of a conductor to current of 1 ampere when the potential difference across the ends of the conductor is 1 volt. Okay, let us also know the definition of potential difference. Potential difference is the work done by a cell or a battery to move 1 coulomb of charge across the ends of a conductor. The work done by a battery or a cell to move 1 coulomb of charge across the ends of a conductor. I can explain that with this diagram. If I have here a cell, this cell is going to push the charge to move from the electron to move from the negative terminal through this connecting wire and come to the positive one. But to do that, this cell has to do work, has provide the force that pushes this electric charge to move through this. So that work the cell does, or the work the battery will do, is what we call potential difference. Now that potential difference is the work that is done by the cell or the battery to move 1 coulomb of charge across the ends of the conductor. From here, this is the conductor, even through the bulb up to here, these are the ends of the conductor. So when it moves through this, the work done by this battery or the dry cell is called potential difference. What are the units of potential difference? The potential difference, or PD, is measured in volts. So what is a volt? What is a volt then? A volt is the potential difference across the ends of the conductor when 1 joule of work is done to move 1 coulomb of charge between its ends. Is the potential difference when 1 joule of work is done to move 1 coulomb of charge between the ends of what? The conductor. When the work done is 1, and when one joule of work is done, then the charge moved is 1 coulomb. Okay, then the charge moved is 1 coulomb. So the potential difference, rather a volt, is the potential difference across the ends of a conductor when 1 joule of work is done to move 1 coulomb of charge between the ends of the conductor. You have to practice on defining those terms and understand them, and you master them. We can now look at the factors that affect resistance. When we go back to our resistance, what are the factors that affect the resistance? Okay, if you are to imagine, you have length of the conductor or the length of the wire. If I have a wire, its length will affect the resistance of the wire. Let's look at these two pictures. Here I have a wire of 1 meter and a resistance 1 ohm. When I pass current of 1 ampere through it, 1 meter and resistance of 1 ohm, then 1 ampere will pass through it. But when the length of the same wire is increased to 2, even the ohms or the resistance will be 2 ohms. The amount of current which enters, which it allows now, is 0.5, has reduced by a half, has reduced by from 1 to 0.5, but yet the length increased to 2. So implying that when the length increases, then the resistance is increased, which lowers the amount of current which passes through the conductor. So therefore, from this analysis, we can say that the resistance of a conductor is directly proportional to the length of the conductor. So R is directly proportional, implying that resistance increases with increase in the length. As the length of the conductor is increased, then the resistance of the conductor is also what? The longer the wire, the higher the resistance. The shorter the wire, the lower the what? The resistance. Another factor that affect is the thickness, or call it cross-sectional area of the wire. Here we have, what do I mean by cross-sectional area? This section here is the cross-sectional area of the wire. This one. Now, here we have the wires of the same length, but this wire here has 2 ohms, but this one, which is wider, has 1 what? Ohm. So what do you observe from this? That the larger the cross-sectional area, the lower the what? The resistance. And the smaller the cross-sectional area, the higher the what? The resistance. So therefore, from here we get a statement that the resistance of the conductor is inversely proportional to the cross-sectional area. Inversely proportional. So as the cross-sectional area increases, the resistance decreases. The thicker the wire, the lower the what? The thickness is this cross-sectional area here. So the thicker it is, the smaller the resistance, or the lower the resistance. So the relationship there is inversely proportional. The third factor is temperature. Oh, think about it, temperature. Okay, now let's consider 2 wires, S and T. T is being heated and S is not. So wire with higher temperature has higher resistance. Now this one will have a higher resistance than the one which is not heated. So that means that the resistance of a conductor increases with increase in what? In temperature. So for example here, a pure conductor like copper, its resistance increases with increase in temperature, while there are others whose resistance does not increase when temperature increases, and these are called semiconductors. Semiconductor like silicon, the resistance increases with decrease in temperature, or it decreases with increase in temperature. That is for semiconductors. Here there are 2. It's either way. For pure conductors, increase in temperature increases resistance, but for semiconductors, increase in temperature decreases what? Resistance. And the last factor which I'm going to tell you is the nature of the conductor. Nature of conductor, or we call it resistivity in physics. Of course, by nature, there are wires of different material. We have a wire of copper and then a wire of aluminium. Okay, have here these wires which are made of different what? Materials. So for wires which have different materials, even if they are of the same length and the same cross-sectional area or the thickness, the resistance will still remain, will be different. The resistance will be different. So that means what is now affecting the resistance is the nature. So here we can say different conductors by nature have different resistances due to their different conductivities. For example, a copper wire and an aluminium wire of the same length and same thickness, even if they are the same room temperature, will have different resistances. So the only factor now being affecting that is their nature. By nature, what they are composed of will make them to have different resistances. So those are the factors that affect the resistance of a wire. If you can summarize with me, we have the length of the conductor, and we have the cross-sectional area or the thickness, we have the temperature of the conductor, and lastly we have the nature of the conductor, which we simply call the resistivity. Having looked at the factors that affect resistance, can now look at the resistors themselves. What are resistors, or what is a resistor? A resistor is an electrical component or device designed to have a known value of resistance in a circuit. An electrical component or device designed to have a specific value, or those can be a combination of them, of components or devices which are specifically designed to have certain amount of resistance in order to oppose or limit the amount of current flowing through, the circuit or through it, and these are called resistors. What are the types of resistors? We shall deal with basically 2 types. We have fixed resistors and we have the variable resistors. Fixed resistors and the variable resistors. What are fixed resistors? A fixed resistor is a resistor which has a specific value of resistance and we cannot change it. We cannot change the value. If the value is 2 ohms, it will remain 2 ohms. If it is 4 ohms, 1000 ohms, such a resistor is called a fixed resistor. And in our circuit, this is the symbol of a fixed resistor. Either this one, the old fashion, the new fashion is this one. So you will choose which one you prefer. But however, these are pictures showing resistors whose resistance is fixed. They are colored. If you check the radially at some of these resistors, and later we shall learn what these colors mean, which we shall call the color code of resistors, and we know how we calculate the value of resistance of these resistors. But just talk about fixed resistors. This is the symbol in the circuit. Example include carbon composition resistors. They are those that are composed of carbon, and then we have those ones, a wire is wound on something and it has fixed resistance, so we call it wire wound resistors. Variable resistors, as the word suggests, vary, to change. So to change means that these resistors whose values of resistance can be changed through a dial, a knob, a screw, manually by a proper method. But by any means, if you can change the resistance of that resistor, then that resistor is called a variable resistor. Okay. In these types of resistors, there is a sliding arm which is connected to the shaft. Now the examples of this are, we have a rheostat. Now this is the sliding arm. Once I move it from this end to this end, I will be increasing resistance, and I move it from this side to this side, I will be reducing. So a rheostat is an example. We have a potentiometer which has this dial here. The wire is wound here, so whenever you move, you either increase resistance or you reduce, making the resistance of the device to be variable, to vary. And so we have, these are examples of variable resistors. Where are resistors applied? What are the applications of resistors? Wow, there are so many. Of course, as we have seen, to control and limit current, the amount of current flowing through a circuit, to change electrical energy in the form of heat, to act as a shunt. To act as a shunt, what is a shunt? A shunt is simply a resistor which is connected in parallel or across a small a device which measures small currents, like a galvanometer, to act as an ammeter. We shall learn that later. As an amplifier also, rather a multiplier in a voltmeter. In a voltmeter, this one also, it can make a very small galvanometer which measures small currents to be able to multiply it to a voltmeter. So that one we shall connect a resistor. That's what it's called, a multiplier. To control the temperature, to control voltage or the potential difference. Shall see later in experiments that if you want to control, you use a resistor or the rheostat as a protective device or for protective purposes. For example, a fuse. In a fuse, which is a device, which is a resistor of just specific value of, it only allows specific amount of current to pass through it. The moment you go beyond, it will melt or it will blow and protect the device from blowing. We use resistors in laboratories, so you'll see later. And now all those appliances at home, the heater, the immersion, the radios, they have resistors. They are widely used in electronics, in the phones. Those have resistors. So these are the applications of resistors. Now, having known the resistance factors which affect the resistance, we talk about the electric circuit. What is the electric circuit? Electric circuit is simply the path of transmitting electric current like a transmission line. An electric circuit includes a devices like includes a device that gives energy to decharge the particles. Those are the electrons. So, and for example, a dry cell and a battery, that one, as we said, it does work to push the charge, so it has to be in a circuit. Then also we have lamps, electric motors, computers, resistors. All those connecting wires or transmission lines are connected in an electric circuit, or to make an electric circuit. Note: current must have a complete path of conductors if it is to flow. Now this circuit, when arranged, has to be completed. So when you put a switch, the switch has to be closed for current to flow. That is what I mean here. Now, but before we go into arranging electric circuit, let us know the devices which are needed or which are used. Some of them, of course, a dry cell here as a direct current source, DC. The symbol is this one. The longer bar here it stands for positive terminal, and the short bar negative terminal. Drive charges through the component. This one is to push the charge, to do work, to move those charges. Then there's the battery here. These are commonly known as batteries, but the scientific name for this is an accumulator. An accumulator here is also a DC source, direct current source. It's a group of cells. That's why I put 1, 2, 3. There can be even more. It's a group of what? Cells. We have connecting wires. These are the transmission lines to provide the path of the charges. The switch, which completes and breaks the circuit, turn on and off, or to let the current flow and not to flow. Then we have the resistors. These ones we've talked about them. This is the symbol for fixed. This is the symbol for variable. Now, variable resistor, like a rheostat, has an arrow crossing it. Now that means that this arrow stands for the sliding contact, which is moved from one side to another. Then we have instruments which measure current and PD. Ammeter, when it has 8, means it is an ammeter. The symbol is that. And it has V, it is a voltmeter. This is the symbol to measure the PD. A galvanometer for measuring small amount of current. We have G. We have devices like diodes. Diodes just allow current to flow in only one direction, and that's the symbol for diode. A bulb for lighting, it's the symbol for bulb, gives light. Also we have capacitors. Capacitors, their symbol, these bars have the same size. The capacitor store a charge. You have already seen this. If you have ever checked, or I give you a task to check, but don't spoil your daddy's radio, you will see these devices here called capacitors. They store a charge. We have a power supply. This one can, when you see this symbol, means an alternating current. The current moves forward and backward, to and fro. And then this is DC. Okay. If you have wires crossing over the other, then you have form a junction, and in a circuit we represent that junction of crossing wires as this. A transformer. This transformer, this is the symbol which steps up and down the PD, or the potential difference. So those are some of the devices that are used in connecting current in an electric circuit. We shall be using some of them in our lesson. So we go back to our arrangement of a simple circuit. A simple circuit should have a device which provides the charge, and that's the dry cell or the cell or a battery. Okay, connecting wires, variable resistor, a rheostat, ammeter, a resistor, a voltmeter. A voltmeter is connected across. It's not in line like an ammeter like this to measure PD. You connect it across. And the switch. Now when the switch is open, it's not closed like here. This circuit is called an open circuit. When the switch is open, the circuit is called an open circuit. But when the switch is closed, like here, then the circuit is called a closed circuit. So you have, when you arrange your circuit, you ask yourself, do I have an open circuit, do I have an open circuit, or I have closed circuit? Depends on what you have done. Okay, and here current now is being delivered, but here current is not moving because the switch is, and the circuit is not complete. Here the circuit is complete. Yeah, so that was just showing you a simple circuit arrangement. But let us go into Ohm's law. Ohm's law looks at the variation or the relationship between potential difference PD with current in a conductor. And what does it state? What does it state? Ohm's law states that under constant temperature and other physical factors, the current flowing through a conductor is directly proportional to the potential difference across its ends. That if the temperature of the conductor is kept constant, and the other physical factors like length and cross-sectional area or thickness are also kept constant, then the current through the conductor is directly proportional to the potential difference. Now from that you can see that I is directly proportional to V, or V is directly proportional to I. Now if we remove the proportionality sign, we put equal sign, then we have to put a bracket. That is your simple mathematics. We put the constant K. That constant K is called constant of proportionality in mathematics. But for us in physics, we shall look at what really has not changed when you are changing I and V. And since the temperature was kept constant, the physical factors were also kept constant for that conductor. The length is not changing, the thickness, the area is not changing, the temperature is not changing. It means you are not changing the resistance. So the constant in our conductor now becomes what? The resistance. So we shall substitute. Hence, where there is a K here, we shall substitute there R, because our resistance in that conductor has remained constant, because all the factors that can change it have remained what? Constant. So hence from here we shall get the Ohm's equation, which is a very important formula in electricity, that V is equal to IR. Please, this formula here, V is equal to IR, is very important. You have to get it, memorize it, let it be at your fingertips. It is very important, as you will see later. V is equal to IR, which comes from the statement of Ohm, or the Ohm's law. And also, if I make R the subject, I get V over I. From here I can define this R, that is the ratio of the potential difference to the current flowing through the conductor, because I'm dividing the two. Okay, so that's the resistance of conductor. I'm finding the ratio of the potential difference across the ends of the conductor to the current through it. How can we verify that experiment? Now, for us scientists, if somebody came up with a law or a principle and was able to do, we always ask, can we do the same and we get the same results? Yes, if we can do the same, then we have proved the law is correct. So how can you in your laboratory verify that Ohm's law is correct? Okay, so we are going to describe an experiment to verify Ohm's law. So we have arrangement of the circuit, whereby simple circuit like that, we have an ammeter, voltmeter, that. Okay, in the lab we would have a setting of this sort: an ammeter, a rheostat which is here, a voltmeter which is here, a resistor, the dry cell, a switch. So this is how it will be set on your table. Okay, then what do you do after you have arranged? The circuit is connected as shown above. I've showed you that already. The switch is closed. Remember, to complete the circuit, the switch must be closed. So the switch is closed, and the resistor P is adjusted to stable values of current I and the potential difference V. read from the ammeter and voltmeter respectively. So after you have closed, you don't just start right away. Adjust the rheostat slowly. Adjust the rheostat until you get certain values of I. Let me take you back a bit. After you have closed, like here it is closed now, here the switch is closed, then you adjust this rheostat, move this slide, okay, and these pointers on the ammeter and will move up to certain way, then you stop, read those values of I and read the value of V. Okay, after you have read them, then the experiment you repeat by adjusting. You get other values of I and other values of V by adjusting the rheostat, and then the results are tabulated. To tabulate it simply means put your results in a table. So you will have which column? You will have a column of I in amperes and you have a column of V in volts. So after you have obtained like 5 to 6 values, pairs of values, then you can plot a graph of I against V. That graph is plotted, and when that graph is plotted and you obtain a graph, that will be obtained is a straight line through the origin. It simply shows that I is directly proportional. A graph of this nature, I, if it is this, then this shows that I is directly proportional to V, and hence Ohm's law is verified. Hence Ohm's law is verified. Ohm's law has weaknesses, it has limitations. There's where it doesn't work. So what are the limitations of Ohm's law? I've not written them here, but you can now just listen and note. Okay, you have to pay attention. Okay, now what are the limitations? One, the law stated that under constant temperature and physical factors, I is directly proportional to V. So that simply means that the law does not work when those factors are not kept what? Constant. The law does not apply when the factors are not kept constant. So the limitation is that the law only applies to when the temperature is kept constant and when physical factors are kept what? Constant. That is when the law is applied. Ohmic and non-ohmic conductors. Now there are conductors that obey Ohm's law and there are conductors that do not obey Ohm's law. Conductors which obey Ohm's law and have constant resistance, when the voltage is varied across them or the current through them is increased, the conductors are called ohmic conductors. Basically, these conductors which abide by the I is directly proportional to V, the moment they abide or they obey, they are called ohmic conductors. A graph of current versus voltage across these conductors will be a straight line like the one I showed you, or this one here. Once the graph is like this, then these conductors obey Ohm's law and they are called ohmic conductors. Examples include copper wires, nichrome wires, Constantine, as you see in the lab. Those obey Ohm's what? Law. However, not all conductors obey Ohm's law, and those that do not obey are called non-ohmic conductors. Do not obey. When you plot a graph of I against V for these conductors, it is not a straight line through the origin. It is not. So it's not. It is a curve like this one here. So you can see that this is a curve instead of a straight line like the one above, the one we saw above. This is a curve. Okay, so this such a conductor here is non-ohmic. Examples are many. Okay, there are many. There is a filament lamp which gives us this nature of the curve. Filament lamp, a gas discharge tube, this nature of the curve. A thermistor. We have a thermionic diode. Those diodes, semiconductor diodes, they do not obey Ohm's law at all, and they give us this nature of curves. And I've not brought these curves for fun. You try to master them because you can be asked to draw or to sketch some of this. Any of this we can ask you to sketch. There's another curve here. dilute sulfuric acid, an electrolyte. This electrolyte here does not obey Ohm's law. It gives us a curve of this nature, and then inert gases like neon gas also do not obey that. So Ohm's law works for actually very few, for some few conductors like copper, like constantine, like nichrome. Those wires obey Ohm's what? Law, or those metals, but some do not obey. Okay. Connection of resistors in a circuit. How are resistors connected in the circuit? We don't just throw them there. In that circuit there, you don't just throw resistors there or connect far. You don't connect anyhow. Okay? There are two ways in which resistors are connected. And the first one, you can connect them in what we call a series connection. What is a series connection? Here, resistors are said to be in series if they are connected end to end. If they are connected end to end, okay, so that the same amount of current passes through them end to end, and the same amount of current will pass through them. Let us look at this picture here. This resistor, this and this, are connected from this end to this end, from this end to another end. So that's what we mean by end to end. And when current is delivered by this battery here, the same amount of current pass through this connecting wire, through the resistors, back to the battery. So to bring this here, from here current will come. It does not divide at all. Passes through this resistor, comes here, it comes here. The same amount of current. So these resistors are connected in series. How do we get their total resistance? Now if we consider three resistors, R1, R2 and R3 connected to a battery of PdV as shown above, so that's the PD of this battery here, BV, which is here. So what do we say? The total PdV is equal to the sum of PDs across individual resistors. This total PD will be equal to this V1 plus V2 plus V3, which are the PD across each of these resistors. V1 plus V2 plus V3 is equal to V, which is the total PD. But we also saw that the current which is delivered by this battery here is the same through all of them. So current I passes through all of them in series. So from Ohm's law, if you get our equation, remember IV, so shall have IR1 plus IR2 plus IR3. This is V1, this is V2, this is V3. Okay, so when you pull I out or factorize, shall have this expression. When you divide by I through, shall have V over I is equal to R1 plus R2 plus R3. But V over I is equal to R, where R is the total resistance. But V over I is equal to R, which is the total resistance, because it's a ratio of the PD over the current. You get R. So in the whole circuit, that is R. So therefore we can hence say that the total resistance R is R1 plus R2 plus R3. This total resistance, as you see later, it is also called effective resistance. So for resistors in series, connected in series, the total resistance is now, you can see that is the sum of the individual. It's the sum of the individual resistances. When we add, we just add and we get a total resistance. How about for parallel? How are resistors? Resistors are said to be in parallel connection if they are connected side by side, so that the same PD, same amount of PD is across each of the resistors. What do we mean by side by side? If I have this side by side, not end to end, this side to this side. So here, these are the resistors in this picture in the real setting. So you have this. When current moves from this side, it will reach here and here, then it splits. When current is split, it means that those resistors are in parallel. Like from here, I are split to I1, I2 and I3, but the PD across each of these resistors is the same. That is the characteristic. So how do we get the total resistance? The total resistance, we have seen that the total current supplied by battery is equal to the sum, because it is split I1 from here, this I1, I2 is equal to I1 plus I2 plus I3. Okay, but the PD across each of them is the same. This V is the same. Okay, so from V is equal to IR, so I can make I the subject and say I is equal to V over R. So what is I1? We can get I1 by dividing this V by R1, which is V over R1. I2, this V over R2, which is this one here, and I3, V over R3. Why? V is not changing because it is the same. Unlike in the series where it was I which is the same, here it is V which is the same. So when you substitute in this expression here, so we have I is equal to V over R1 plus V over R2 plus V over R3. Pull out V and divide. You have 1 over I over V is equal to 1 over R1 plus 1 over R2 plus 1 over R3. But V is equal to IR, where R is the total resistance. So this is this PD and this is the current. So if I want to get this PD, I can get the total resistance R times this current, which is that. Okay, so when I substitute, I get this expression, and you cancel out this I will cancel with this one and remain with 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Thus, from this now expression, members, dear learners, from this expression, what do you note? That for resistors connected in parallel, the reciprocal of their total resistance, the reciprocal 1 over R, is equal to the sum of the individual reciprocals, or the sum of reciprocals of individual resistances. So 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. When you compare it with the one of series, the other one was summing up the resistances themselves, but here we are dealing with the reciprocals. Okay, now if we remove one resistor and say let's consider only two, so I have chopped off here the third resistor which we got, so we have that. When you simplify this, we take the LCM R1 times R2, have that, we shall end up with R being equal to R1 times R2 over R1 plus R2. This one can be summarized in this statement, that this is the product of the resistances over the sum of the resistances, but this is only when the resistors are what? Are 2. When they are 2. Okay, now let us look at an example of calculating effective resistance or total resistance. Okay, find the effective resistance of the following diagrams. This one. Okay, as you can see here, these are connected end to end, making this a series connection. So we shall simply add. Okay, shall simply what? Add R1 plus R2 plus R3, this plus this plus this, we get the final answer to be 9. 1 plus 2 plus 6 to get 9 ohms. Let's look at the other side. Now this diagram here, again they are also connected end to end, though not in the same line, but this end connects to this end connects to the other, making this also in series. So we shall use this formula of addition, and 3 plus 10 plus 5, and we get 18 ohms. Okay, total resistance in the when you look at this, they are not the same side by side, they are connected side by side. So for example, these are 2, these are 3. So the solution, A has 2 resistors in parallel, so this is a parallel arrangement. Okay, so what should we do? Like we said, for 2 resistors in parallel, we don't have to go further, we just say product over sum. multiply the 2 and also the over addition of the 2. So 10.4 times 8.6 over 10.4 plus that, and then this gives us 89.44 over 19, and we get R to be equal to 4.71 ohms. That is for only part A, where we use the formula for two resistors in parallel and get this value. We continue further to our second question. Upload the diagram back here. So here these are 3. When they are 3, you don't use product over sum. You go the long way. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So we substitute in 1 over R, 1 over R1. This is 2 plus 4, 1 over R4, rather 4, 1 plus 1 over 6. And you simplify that. It should be simple for you senior 4s or senior 3s. This is some simple mathematics for you. The LCM is 12. Simplify, we shall get 1 over R is equal to 11 over 12. But we don't want 1 over R. We want R itself. R. So what do? We either cross multiply and find R, or just take the reciprocal. And the reciprocal will be 12 over 11. 12 over 11, and giving us 1.09. 1.09. Wow. Is there anything that you notice here? Oh yes. Look here. The total resistance is smaller than the resistance, the resistances of each of these. Do you see that? The smallest has 2. We even have 4, we have 6. But the total resistance is 1.09. Isn't that funny when you are getting total resistance? But yes, that's what we have got. Now, this tells us something, that when resistors are connected in parallel, actually the total resistance is reduced. So much reduced that it is even smaller than the value of resistance which had the slower value. Here I had 2, we have 2 here, but the value here is 1. It is even much smaller. Now, because the total resistance is reduced, it is for this same reason, members, that most of the appliances, if you want to reduce on the resistance and increase on the current that flow through them, then you connect those resistors in what? In parallel. And it is for the same reason that the bulbs in house wiring, the wiring of the bulbs in the house is in parallel. So you can be asked, explain why bulbs are always wired in, are connected in parallel. It's because to ensure that their total resistance is reduced and more current passes through them. And when more current passes through them, then the bulbs will be brighter. Okay, bulbs will be what? Brighter. But for resistors, you saw, for resistors in what? In series, for resistors in series, instead the resistance increases because we just added. So if you connect resistors in series, the total resistance becomes high and less current passes through them. So series connection is always not preferred in house wiring. Example 3. Determine the effective resistance in the diagram below. Good. We see the diagram. Now this diagram has this resistor, but has this which are connected side by side. That means these two are in what? In parallel. The 12 ohm resistor and the 4 ohm resistor are connected in parallel. And since there are only 2, so let's first get the total resistance for them before we add this one. And so I'm calling it RP, the total resistance for resistors which are in parallel. Since there are 2, product over sum. Product over their sum. 12 times 4 over 12 plus 4, giving us 48 over 16. And we shall get RP is 3. So these 2 resistors which are in parallel reduced to 3 ohms, and when they have reduced to 3, then that resistance RP now is in series with the 6, and therefore we shall just add and say now 6 plus 3, and we get the total resistance of the whole circuit as 9. I want to emphasize here again, this one and this one, the 12 and the 4 are in parallel. We first deal with them, get their effective resistance for only these two by the formula that we now know, before we add to this one, before we add to this. Is that okay, dear students? Hope you've understood that. So for that, you can try yourself, can exercise yourself, try to do these numbers. This number 1, find the total resistance, see whether the circuit is a connection is a series or is parallel. When you work out number 1, you also work out number 2 and 3. Okay, these are questions for you to try out and consolidate the idea of calculating total resistance, or what we call effective resistance. Dear students, everything, don't assume that you have known, don't assume that you have understood. Check yourself by working out these numbers and cross check. We promise we shall mark the numbers, we shall mark your work, and you'll get a feedback. Test yourself, and only don't rely only on my exercises. Please get textbook and look for other questions. Okay, look for other questions and work them out. They will help you get to understand the concept which you are teaching much more better. Do not be lazy, dear my girls, my boys. Don't be lazy. You work out these numbers, and you'll pass. You'll understand the things. You'll be better engineers. You'll be better doctors in the future. Okay, you have to know, is it a series arrangement or is it a parallel arrangement? If there are 3 in parallel, what do I do? If there are 2 in parallel, if there are more than 3, what do I do? You use the general formula. Okay, let's go further now. These further examples are utilizing Ohm's equation to find current and find voltage, because we've just been calculating resistance. Now we want to see, can we use Ohm's equation to find the current and resistance? Oh yes. Example number 1, find the current in the circuit. This is the circuit. So what is given in the circuit in our solution? We have V, it is 9 volts here, but there are 3 resistors, so R, there are 3. What do we pick? On this 10 or 5? No, we pick all of them and we get the total resistance. So we add, since they're in series, 3 plus 10 plus 5, and we get 18. So since we now have the total resistance, we shall quote our formula. V is equal to IR. V is 9, is equal to 18, which is R times I. So therefore I is 9 over 8, and get 0.5. So this battery here is delivering current of 0.5 through DC resistors. Okay. Number 2, a PD of 24 volts from a battery is applied to a network of resistors in the figure below. Now these are many, there are 3. 1, find the effective resistance of the network. 2, the current through. 3, the PD across the parallel network. 4, the current through the 6 ohm resistor. Be very attentive here. Now this has many questions in one. We are going to play around this circuit here together. Okay, I hope by the end of this you will have understood. Okay, if you are tired, you can first pause and take some water, then you come back. So because I want you to understand these calculations of current very well, and they are very simple, as you'll see. Okay, you paused, now you all come back. So we continue. So how do we get a total resistance? Effective resistance, as I told you, is the same as the total resistance. And here you can see that my solution we have those this and this are in parallel. 6 ohm and 12 ohm are in parallel. Okay, because when current comes here, when it reaches here, it will split and it will divide, so making this to be in parallel. So we first handle it that. So when we handle that, we shall say 6 and 12 are in parallel. Since they are only 2, product over sum works for us, and we get 72 over 18, which is equal to 4. Then we add 8 plus 4, we get 12. So that's the total resistance. Simple. It's the total resistance. Now current through the 8 ohm is equal to the total current delivered by the battery. Now those 2 resistors, the 6 and the 12, as they were connected, have reduced to 4. Have reduced to what? To 4. But now I want to get the current. So which current will pass through here? That is the same current, or that's the total current delivered by the cell, by the battery. So we shall get the total current with the same current which passes through the 8. Okay, how do we get it? Our formula is V is equal to IR. 24 is equal to 12. Why are we using 12 but not 8? Why? Because that current is also passing through this 4, which was the total resistance of the 2. So we use 12, not 8. So I is 24 over 12, and I is 2 amperes, which is the current. Current is therefore 2 amperes. That current which is being supplied will pass through here and will pass through the 4. And actually not the 4, but the 2 will be now shared to go through the 6 and will go through the what? The 12. Okay? And now the PD across. The PD across. How do we get it? You see, that current was now passing through here, and when it reaches here, it will divide. But what is this PD across parallel arrangement, which I have called VP? How do we get it? We say VP is equal to I, which is the total current times. We use the total resistance we obtained for only 2. For VP, we use the total resistance we obtained for the 2 resistors which were in parallel. So we shall say I times RP. So from there, we say VP is equal to, VP means the PD across the parallel arrangement. So VP is equal to 2, which is the current we obtained, times 4. Not 6, not 12, but we use the combination which we have got as 4. So times 4, and you get VP is equal to 80 volts. So this PD here of 80 volts, and it's the same here and the same here. If this one have obtained 80 volts, the remaining will be here. So out of the 24, what will remain? 16. So 16 will be by this 8 ohm. Okay, so we go further. How about the current in the 6 ohm resistor? Now that PD across the 6 ohm resistor is the same as the PD across the parallel, the PD across this is the same as this VP, which we have calculated here, which is 80 volts. So now, if I want to get the current, we shall just divide this VP by the 6 to get the current through the 6 ohm. So we shall say I1, if we are to call it I1, then VP over 6, and I1 is 8 over 6, giving us 1.33 amperes. If we wanted for the other one in the 12, then we shall just have said 8 over 12, and we get the answer. Okay. However, there is more work, so you can try on your own. You can try to find the current through the 12 ohm. I've already told you, just divide the 8 now out of 12 to get the answer. And then so you can find to get the PD across the 8. How do we get? We have obtained the current and we have the resistance. So you can do that and get the values. Okay? Yeah. I hope you have understood that. And we go up to my final example here. Find the value of EMF V of the battery if the ampere reads 2 if the ammeter reads 2 amperes in the circuit below when the switch is closed. Where is the circuit? Yeah, there it is. So what is this value? This time this value is not given, but the current is given 2. So this ammeter reading is 2, means it reads current. So what do we do? Again, we see that this one and this one are in parallel. We first handle them. Product over sum, 6 times 4 over 6 plus 4, 24 over 10, giving us 2.4. for only these two which are in parallel. And now the total resistance we add, now this value we add to this 3.6 plus 2.4, we get 6 ohms. So this is the total resistance. Having obtained the total resistance and you have the current delivered, so what will be V? V now will be equal to IR, giving us 2 times 6, which is this 6 is the total, which get 24. So this battery here supply has a PD of 24 volts. Okay, has a PD of 24 volts. I hope I've made some sense to you. I hope you have understood what I've worked out here. Please remember that this one has to be handled first before we add. We have to look at a circuit where there's a parallel arrangement. You handle the parallel arrangement by getting the total resistance there before you look into the series arrangement, and you shall get. And remember how I told you that V is equal to IR is very important in calculating these things. Okay, so I'm going to leave you with yet another exercise to practice yourself on these numbers of Ohm's law, whereby you calculate the current, you know how to calculate the total resistance. That is example exercise 1, number 1. Then there's also exercise 2. This one have to be very careful. There's where the switch is closed, K1 is closed, K2 is open. What does it mean? Yeah, we shall harmonize in case you fail to get it right, but I want you to first try, my dear students. Okay, you have to copy that work. There's also 3, which is asking for the total resistance, the ammeter reading, and the PD. Ammeter reading is the current. When they ask for ammeter reading, they're asking you to find current. When they ask for voltmeter reading, then calculating, you're going to find the voltage. Yeah, thank you very much for listening. Next time we meet, I'll be talking about this electromotive force, and in our next lesson we shall meet virtually, I mean, of course, what potential difference and internal resistance of a cell or a battery. Okay, I hope you have understood my lesson and you're going to try out those exercises. Thank you very much for listening, and have a nice day.